we go. So section 3.5 is compound Boolean expressions. So the main thing that we're introducing here is, check this out. We can have two or more things put together with an and the and symbol isn't the word and, it's these two ampersands, which is shift 7. And the other option is we can have an or, which is two vertical lines. That's shift backslash. It's over by the enter key on your keyboard. There's a little vertical bar. So two vertical bars mean or, and two ampersands, the shift 7, mean and. And so this thing right here, if guess is greater than lower and guess is less than upper, that's making sure it's within a little range. And another way to do the same question, although the results are, these are not equivalent, is to say if guess less than lower or guess greater than upper, your guess is out of range. I think that because these aren't greater than or equal to, they're not technically doing exactly the same thing. Like what happens if guess is equal to lower? That's all I'm saying. Let's not worry about that right now. I wasn't trying to make these equivalent. I was just showing you an and showing you an or. You can do this sort of thing by nesting if statements. So check this out. Here's one. If guess less than upper, and then inside of that if, I've got if guess greater than lower, then it can say it's within range. Like that's one way to do it. Certainly that's not wrong. You have a lot of curly brackets, but compare that with this one down here. It's just two lines of code. If guess greater than lower and guess less than upper. It's a little easier to process, with this example. We also have the not operator, which is the exclamation point. And it flips whatever Boolean expression comes next. So by flip, I mean if it was true, it's false. And if it was false, it's true. So right here, we're asking the user to enter something, and we're checking if it's equal to yes. But the not here means it's the opposite of this. So if I did enter yes, then entry.equals is true, but then the not symbol means that it's looking for it being false. So this code works like it will only trigger if they didn't enter yes. Here's another example. Boolean is good equals true. So I'm setting up a variable called is good. I'm putting true in it. And then I'm running 3 tests in a row. If entry.index of Liger is -1, then set is good to false. If the length of the entry is less than 10, set it to false. And then I'm checking, hey, how's my variable? Is it apparently I needed it to say Liger in it, and I needed it to be greater than 10 characters for it to be valid. You could do this all in one giant if statement, but I think I was trying to use the not symbol here. You can look at it longer if you want. This last example is an example of something called a flag variable. A flag variable is when you set a variable to something, and then you do a bunch of stuff that may change that variable, and then afterwards you check, hey, how's that variable doing? So rather than trying to do it all with the big if thing, you can sometimes easier just set up a variable. You could say, hey, I'm going to set this integer variable to 1. And then inside here, I may or may not change the value. And then afterwards, you can say, is it still equal to 1? And that would mean to you, because you designed the code, everything's good. But if it was 0 or bigger than 1, you'd be like, okay, now I know what to do because I changed the variable. So that's called a flag variable. It's one way to have to, yeah, so here I rewrote that whole thing with, I wish I could make this go away. I wish I had, there we go. I rewrote all this in a single line, and you go, well, that's easier. Sure it is. But sometimes it can get a lot crazier pretty fast, and it's nice to have a little flag variable instead of having to make, if you find yourself doing too many ands and ors, you're probably writing bad code. Nobody wants to read that kind of stuff. I try to limit mine to 2, an or an and, but every once in a while you have more than that. So here's a totally cool thing. It's called short circuit evaluation. Short circuiting in electricity is usually bad. It means wires have touched that aren't supposed to, and then you get a big spark, and sometimes you get a fire. In Java, it's not a bad thing. What it means is we're not completing the line of evaluation. We're bailing out early. So there's two situations where you can do this logically. Here's an or example. Check this out. If guess is less than lower, or guess is greater than upper. Now let's just say guess is less than lower. It's going to print this thing because it's an or. They don't have to both be true. So let's just say guess is less than lower. Java actually stops evaluating. It's like, I'm going to save myself milliseconds. I'm going to save myself time and energy. I'm not going to evaluate the rest of this thing because I know I'm going to print it. So I'm just going to go and print it. I'm not going to keep checking things. That's called short circuit evaluation. This is how it works with an or. If the first part of the or is already known to be true, then it doesn't check the other part, because an or is like, if either one of these is true, I'm going to proceed. But if the first one's true, it just says I'm not even going to check the second one. And with an and, if the first one is false, then it knows it doesn't have to check the second one, because an and requires both of them to be true. So in an and, if the first one is false, it doesn't check anymore. It's like, well, it's an and. I don't need to go any further. I mean, and you think about what it's saving. It's like it's saving the tiniest little piece of time, and maybe electricity, probably not. But anyway, it's just not, we don't care about that time, but logically it's kind of handy in some cases to have Java do that. Sometimes you'd have an expression where the second half would crash if the first half wasn't true, like a dividing by zero situation. So it's not very common, but you could say, hey, let's make sure this variable is not zero. And then let's make sure when we divide it, we get the answer we want. That's an example where if the first thing was zero, then it's not going to keep checking, because anyway, if the first part is false, Java doesn't keep checking, because if it's an and, there's no point. Okay, so I'm going to post the Day16 compound Boolean REPL assignment, and we also have a slide, a Google form. We'll practice. Okay, so truth tables. How many of you have done truth tables before? 5 of you. Awesome. So, folks, Boolean expressions and if statements can give rise to truth tables, and they can be complicated, but they are actually mechanically very clear and not hard to understand. They can be hard to do well, but really big ones. But in its most basic situation, a truth table, this is the most basic truth table I can think of. Think of it as two Boolean conditions, two Boolean variables, A and B, like is X greater than 7 or something. And we're going to say, these are all the ways that you can combine them both being true or false. So what we usually do is write true, true, false, false under the A column, and then true, false under the B column. But these are the 4 ways you can arrange two things that are either true or false. Yes? We're not talking about binary numbers, but yeah. So the first column holds values for A. We're talking true, true, false, false. And the second column holds the B values. And these are all the ways you can combine true and false with two variables. So the first row represents where both A and B are true. See, that's why they both have T's, TT. And the second row is where A is true and B is false, and so on. And you nearly always start a truth table with these two columns, A and B. And you can, if you don't want to do T and F, you could do 1 for true and 0 for false, 1, 0, 1, 0. Sometimes my T's and my F's, when I write really fast, start to look the same, because I get a little sloppy, and then I'm like, okay, I lost track of what's going on. So 1s and 0s are a lot harder to confuse. So I think on all these, I'm doing T's and F's, but It gets more interesting when you add another column. So, but it's actually not too hard to do. So this is A and B, the same as it's been so far. Now I added an A and B. So, we just learned about this compound operator, right? So you can fill this out by saying, hey, are both A and B true? And if they are, you put a T there. And if, here, are both A and B true? Nope. So we put an F. Are both A and B true? Nope. We put an F. Are both A and B true? Nope. We put an F. So it's not checking, are they the same? It's checking, are they both true? So if we were saying, hey, for any given A or B logical conditions, let's make a truth, let's fill out the column for A and B. There's 3 cases where they're false when you combine them, and 1 where they're true. I'm going to add another column, an A or B column. This is perhaps more forgiving. If either A or B is true, then the A or B column is true. So this top line would get it true. The second row would get it true. The third line would get it true, because each of those has at least 1 T in them. Bottom line would be false because there's no T over here. So here's where you might need to do a truth table. What if you had this Boolean expression, not A and then parentheses A or B? If you're like most people, you can't look at that and go, oh, intuitively, I understand what that's asking. I look at it and think, oh, God, I'm going to make a truth table. So I would start with the A and the B columns, the default 2 columns, just like I've been doing all along. And then what I do is I populate columns out with everything that I don't know from the A and B columns. So not A, that just means the opposite of A. That's going to be 1 item. And then the A or B is another column. And then here's the final thing. The far right column is for me usually, in fact, always the thing that I'm asking, the ultimate thing I'm trying to work out. So if I were me last year making this slide, I would right now fill only out the not A column. Whew, I did it right. So look, I'm doing the opposite of A. So there was a T here, so there's an F, a T and an F. And then I'm doing the opposite. There was an F here, so there's a T here. So it's basically the opposite of what A is this column. And then the A or B column is, we did that on the last slide. It's if there is at least 1 T, we put a true. So that's true, 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 and false. And then for this last column, rather than having to just go, man, I hate myself, and why is there logic, and I wish this didn't exist, you can say, look, all I have to do is look at these 2 columns and them together. That's what our original thing was. We have the not A column right here, and we have the A or B column here, and we're just going to and them together. So F and T, that would be false because they're not both true. F and T, nope. True and true, so we'd have a true on the third one down, and the bottom one would be a false. To get the last column, you can ignore the other columns. We're just looking at these 2 columns. That's how I'd like to do it. Get it to where I'm just looking at 2 columns. I literally put my fingers on the paper, and I'm like, okay, are these 2 both true? If they are, I put a true. And then otherwise I put a false. You can work your way through. So I got a worksheet I want you to do now. I'm going to pause the last part of today. Everybody, there's a cool law, a logic law called De Morgan's law. And it's basically like a mathematical distributive property for logic. And it says if you have an expression like this over here, the not symbol in front, it's not technically the distributive property, but you can think about it. You think, I'm going to distribute this not symbol to each part on the inside. So it becomes not A, and then the opposite of and is or, and then it becomes not B. Do you see that? And over here, if we had not A or B, it becomes not A and not B. You have to distribute, you have to apply the not symbol to each thing on the inside. So you'll have on the AP test, there'll be which of the following is equivalent to this thing. And all they're asking you to do is distribute and simplify a little bit and go, okay, it's this one, you know. So here's one example followed by another example. So if I gave you this and said, please simplify, it would become this. So you don't put a not in front of the num because num is a variable, and you don't put it in front of the modulo because there's not a not modulo operator, but you'd apply it to this not equal because this is like, hey, if you divided by 2 and the remainder was 1, so that becomes you divide by 2 and the remainder is not 1. And then the and here becomes an or, and then this one becomes a not equal to also. So that's one example. Here's another example. This is saying not A equals 7 or B equals 9. So we're going to say A not equal to 7 and B not equal to 9 for our De Morgan simplification. Questions? So just a summary here. A double equals becomes a not equal. Here's one that might not be intuitive to you, but greater than becomes less than or equal to. Because what's the opposite of, if it's greater than, it's not less than, it's everything else that's not greater than. So that becomes less than or equal to. And same with the, less than becomes greater than or equal to. And a not equal to becomes equal to. So here's a little summary. You don't have to memorize these. I mean, if you think about it, what's not less than something? Well, it's everything that's either equal to or greater than. And you'll get used to it. So you don't do the not on int variables. So I've already shown you an example here, but if I said not A greater than B and C not equal to 12, you don't write not A less than or equal to not B, because these are numbers. These are integer numbers. You flip this around. The A greater than B becomes A less than or equal to B. The and becomes an or, and the C not equal to 12 becomes C equals 12. So you don't do not A less than B, because A and B in this case are integers. That's different than if they were Boolean variables. Then you would put the not in front of them. Yeah, here's an example where they are Boolean variables. So look, I made an is hot variable and set it to true, and I made an is windy variable, set it to true. But then I have this expression, not is hot and not is windy. Sorry. You distribute this becomes not is hot or is windy. And of course you can use not with anything that would normally give you true or false, like the dot equals command returns true or false, and you could put a not in front. So this is saying, hey, if name1 is not equal to name2, then do something. That's because name1 dot equals name2 is a Boolean expression. It returns true or false. So putting a not in front of it is basically saying, hey, if this is equal to false, then we go ahead and do our thing. So it can get a little crazy. So here's a crazy looking one. But it's really not that bad. The not applied to this becomes A less than or equal to B instead of A greater than B. The not applied to the and becomes an or. And then my advice is just put the not in front of the whole parentheses part and then do that as another step. And I think you're still going to keep the parentheses. So now we're going to have A greater than or equal to C, and then it'll be an and here, and then B not equal to C. Some of you will find that you can do it all in one line, and that's fine. You don't have to show me your work. You just have to get it right. Okay, and down here it says done. So where we're at here,